Good evening, everyone. Actually, it's one of the coolest talks I was looking forward to. We do first a few public announcements, and it is that actually, if you know something about audio, video, or something else, the guys over there, the angels, need a bit of more help. So if you know something about it, or you want to learn something about it quite quickly, go to the angels, go to heaven, subscribe, and give a few points. It's actually really cool to do. I'm actually heralding here. And the talk we're actually seeing in a moment will be actually about Tor and actually the low-level things that actually being fixed, because it's not that easy, I've heard, and it's actually a really cool thing, Tor, but we need to enlarge the whole ecosystem, because the metadata resistance was really a thing, and the decentralization is also a really big thing. But I will actually give the word to you, but first, a really big applause for Morgan. Thank you.
I'm Morgan. Today we're going to be talking about a little library I've been working on for the past couple of years called Gosling, which you're here. You've probably read the talk title, so I'm not going to read all this out. So a little introduction. I'm a software developer working for Blueprint for Free Speech. Blueprint for Free Speech is an Australia and German-based nonprofit which focuses primarily on journalist protections and legal stuff, but they also develop and maintain the Gosling Rust library, which we're going to talk about today, as well as Ricochet Refresh, which I'll talk about a little bit and was partially the inspiration for this work. When I'm not doing that, I'm also the applications team lead of the Tor project, so I manage a team of software engineers where we are developing Tor browser for Android, Mulvad browser, and a handful of other little things. But I promise I know how to program still. So what is Gosling and what does it do? So at a very low level, it's just a Rust library which allows you to create persistent, or not persistent, but peer-to-peer applications with some kind of persistent or like long-term associated identity, along with all this other stuff. So end-to-end encryption, forward secrecy by default, anonymity by default, hole punching by default, censorship circumvention, client authentication, metadata resistance, as well as some optional application-specific authorization extensions. And I'll get into that later. It is really bumping outside. I don't know if you can hear it on YouTube, but holy shit. So how does it work? So from its sort of like user perspective, each user has a unique ID like this. It's a long 56, 58, something like that, string of random characters. If you want to connect to another peer, and what their application is, you need to share this ID somehow in some other safe channel. And then after completing some kind of successful handshake, you two will be able to talk to each other without actually having to know who you are in reality. Which sounds nice, but how does it work? So it, as you can probably guess, it's built on Tor and Tor onion services. This is not going to be a very deep, in-depth dive into the specifics of Tor and how that works. Other people have done that far better than I can. But at a high level, Tor is a community-run network of relay operators. They all have nodes. If you want to connect to some if you want to connect to some website on the internet, for instance, you build a circuit through the network so that it minimizes the amount of information that is leaked about you to your final destination. And it's constructed in such a way that nobody along the route that you've taken knows enough information about you to figure out who you are, who you're connecting to. It's the basic idea. You can go watch other talks about it, but that's the sort of primitive we're working with. Onion services are a bit more complicated, but they basically take the same sort of core idea of multiple hops through this anonymizing network and turns it on its head and makes it possible for servers to have the same sort of guarantee. So for instance, the New York Times and various other journalists will run an onion service version of their website. And in this way, that gives them a couple of nice properties. One, users can get to their website even if their internet is censored, presuming they can get to the Tor network. The website itself can't be censored by local officials or your internet provider or whatever. In theory, if they weren't just the New York Times, they could go to their offices and say, hey, please turn off your website. But ignoring that, they themselves can't be censored because there's no centralized registrar that says, oh no, you're not allowed to run this service on the Tor network. And they also guarantees the anonymity of the users by default coming to the website, because in order to even get to the New York Times Onion service, you have to go through Tor, which gives you all of these sort of aforementioned guaranteed anonymity protections. So with those two little building blocks, how does Gosling work? So every user has an ID. Surprise, surprise, it's actually an Onion service ID. And this ID serves dual purpose. One, it's your username, more or less, in one of these peer-to-peer networks. And it's a destination that you go to as a peer. So if I'm a peer in this network and I want to connect to some other peer, I just connect to their Onion service, and that's that. But it's also an identifier used for authenticating clients when connecting to other peers. So in this peer-to-peer network, each peer hosts an Onion service which other peers want to connect to, and in order to verify to the server when I'm connecting to them, they say, hey, I have this node over here. By default, you don't actually have any real way of knowing that, because from the server side, it's just a TCP connection that's come in. And so in the context of Gosling, we also use if it's peer-to-peer, I'm running a server as well as being a client, and all the other peers are also running a service as well as being clients. So whenever I, as a client, connect to a server, I can basically prove to them that I own this Onion service through cryptography. So yeah, basically these building blocks, we get end-to-end encryption. All communications between the peers are end-to-end encrypted by default because they go through Tor. They have forward secrecy by default because they go through Tor. They're anonymous because, again, you have to go through Tor. It is impossible to leak your actual identity, your actual IP address when using Gosling, presuming you're not doing something silly like in the application layer once you've already connected saying, hello, this is my real IP address, which some protocols do. But that's why you have to be smart about things and not just tunnel arbitrary traffic through Tor and think you're anonymous. And as mentioned before, there's no central registrar, no signups. You don't need to associate your Onion service ID with a phone number or your passport or anything ridiculous like that. You can just run the software, create an ID, and connect to things. You get hole punching by default. Again, that's just a Tor thing. You don't need to have open ports open on your firewall. You don't need to, forward your UDP connections like it's the 90s or whatever, because all the peers just have outgoing connections to some node on the Tor network, and then from there, all other communications just happen. You get sensitive circumvention. As I kind of mentioned before, since there's, like I mentioned in the New York Times, there's no central authority that can say who can or cannot run an Onion service. All of the Gosling traffic stays within the Tor network. So basically, if you can connect to the Tor network, then you have full access to whatever peer-to-peer network within the Tor network exists, which can be a big if. So suppose you live in a place which blocks Tor, like China or Iran or your local library or the mayor's office, things like that. You can use pluggable transports to circumvent such blocks. So the general idea, I'm not going to go into specifics here, but there's a whole ecosystem of so-called pluggable transports within the sort of Tor development community and the broader anti-censorship, the broader censorship circumvention community. That is built around making these little tools which obfuscate your traffic to make your actual traffic look like something else. So for instance, the Snowflake pluggable transport, which is shipped in Tor browser and a couple other applications, will make your Tor traffic actually look like a WebRTC connection. So any potential censor or someone snooping on whatever traffic is going across the wire will just see, oh, it's WebRTC. They're probably doing a web call to somewhere or a video call or whatever. So you may be thinking like, okay, cool story, bro. So you use Tor to do stuff. That's good job. It's complicated, and I'm getting to that. Okay, client authentication. So I kind of mentioned earlier, Onion services as a server are self-authenticating. If you have an Onion service ID and you connect to it, you can know with some certainty, and I'm not going to go into the details because I don't know them, but this is the sort of cryptographic primitive that we have here, is that if you connect to an Onion service, you can be sure that you've not been machine in the middle. So you know that you are actually getting to the server on the Tor network that you think you're getting to. But the opposite is not true. As I hinted at before, if you are a client connecting to an Onion service, that Onion service has no way of knowing who the heck you are. And in the sort of peer-to-peer context where you want to have persistent identity, you need to be able, as a server, to verify that whoever is coming in and connecting to you is who they say they are. The basic fundamental problem here is that clients don't have Onion service IDs. So how do we make sure that clients connecting to you are who they say they are? To go back a bit, I mentioned an Onion service ID is actually, it's this big long string of numbers. It's actually a public key. It's some sort of representation of an ED25519 public key. And since you have the public key, you also have a private key. With a private key, you can sign things. So essentially, what Gosling does is encapsulates this whole cryptographic handshake of saying, as a client, whenever you connect to a server running Gosling, hey, I'm so-and-so. I own this Onion service that you can connect to, and I can prove it by signing a particular carefully crafted a message. So that's kind of part of the value add here, is that you can verify clients coming in are who they say they are, sort of transparently, without your application or you as a developer needing to worry about how to do that or how to solve that problem. I mentioned earlier, we also have optional application-specific extensions. I'll kind of get into why we have this later, but there are little pieces in the protocol where as an application developer can add on a bit of data and then consume that data on either end and verify or somehow authorize a client to connect to you. So for instance, maybe you have a allow list of clients that you want to suppose you have an allow list of clients that you want to be able to connect to and just reject everybody else. Or maybe you want to do some sort of shared secret thing. Like maybe it's running on your phone and you say, okay, I need you to put this little one-time code in to verify that you are who you say you are, and otherwise it's just going to auto-reject everybody else who tries to connect, et cetera, et cetera. The protocol itself allows and facilitates this sort of customizability. And finally, the other sort of big thing is metadata resistance. So metadata is a very annoying thing in that it exists and it pops up in places that you would not necessarily expect and cause all kinds of headaches around your promises around anonymity and privacy and security. So as I mentioned before, communication contents are fully end-to-end encrypted. Clients' real identities are unknown to each other. There's no way to determine who peers have connected to. There's no centralized server somewhere saying, this person is connecting to this Onion service. That destroys the point. It's anonymous. There is no built-in metadata. You can't go subpoena somebody and say, I need you to give me all the Onion services that are on the Tor network, because we just can't do that. It's not technically feasible or possible. So, we've got all these great properties. What's the problem? So I originally started down this path working on Ricochet Refresh, and Ricochet Refresh is a peer-to-peer instant messenger. It uses Tor Onion services. It has all those nice things. It's end-to-end encrypted, and lets you circumvent censorship, has pluggable transports enabled, et cetera, et cetera. But we had a security review a couple of years ago, which uncovered a annoying problem. So an interesting property of Onion services is that you can connect to them, which, yeah, obviously. But if you can connect to them, the only thing you need to know to connect to an Onion service is what its service ID is, or in the browser context, what the URL to it is. And if you can connect to it, it's online. If I'm running the New York Times, that server should always be online. there's no reason for it to not be online unless it's having technical issues. It doesn't really expose anything. Being able to connect to the New York Times Onion service and determine that it's online or it's offline, really. But the problem is that in the context of an instant messenger, your online and offline status is directly correlated with are you or are you not using the computer, or at the very least, are you or are you not connected to the internet right now? And in some contexts, that can leak a lot of information about you. It can tell you, are you at home right now? Are you using your laptop? What is your sleep schedule? That kind of thing. So it's kind of a big deal. And at the time, we were like, oh, what did I do? Hold on. There we go. So yeah, at the time, we were like, well, shit, what are we going to do about this? Like, this is kind of an unsolvable problem. A side note, little thing at the bottom here, Tor Onion Service client authorization, not authentication, authorization does not fix this. So for those of you who may not be fully aware, client authorization is a little feature in the Tor network that allows users to create Onion services, but have an allow list for who can connect to them. And you might think, this is great. You know, I can just have a set list ahead of time of who can connect to my Onion service at the protocol, like low-level network layer, and not have to worry about any of this. But the problem is that enabling this one is terrible for usability in some contexts. If you're running if you have an instant messenger app, for instance, you want to just be able to say, hey, connect to this address. This is my address. You can connect to me and add me as a friend, and then we can chat. With client authorization enables on your Onion service, you need to say, here's my Onion service. Now I need you to give me a public key so that I can encrypt this thing that will allow you to connect to the Onion service. So one, there's a usability problem, which isn't great. But sometimes poor usability is a perfectly fine and justified trade-off in the context of improving user security, user privacy, whatever. The other problem is that it doesn't work. All it actually does is that, sure, unauthorized clients can't connect to my machine directly, but there's this really nice feature in the Tor network also, which allows you to try to connect to an Onion service, and then it will tell you, this Onion service exists, but you're not allowed to connect to it. So at a high level, whenever you're connecting to an Onion service, you know, you're putting in your little URI, goes to Tor, it goes and tries to find the introduction point on the directory server, which has a whole big old hash table of all the Onion services and what introduction points they're associated with. And then you connect it, then as a client, you connect to an introduction point, which actually is talking to the Onion service you want to talk to. And then from there, it will go and you'll negotiate a rendezvous point where the actual connection sort of happens. With client authorization, the thing that you're downloading from the directory server, this hashed mapped thing, is itself encrypted. So if you are authorized to connect to the Onion service, then you can just go in and grab this thing, decrypt it locally, and then continue on. But if you're not authorized, all you're going to know is, oh yeah, this Onion service exists, but it's encrypted. The information I need to connect to it is encrypted, so I can't actually connect to it. So even though you're not able to connect to the Onion service in this situation, you can still know that it exists, and it has been running at some point in the near past. So it doesn't fix the problem, it just decreases the time resolution, because eventually these records in the hash table will expire once you have logged off, so it doesn't actually fix the problem. So yeah, we have a metadata leak. We have coined this sort of thing as cyber stalking, where a malicious third party can cyber stalk you, sort of figure out, are you online or offline at a given point, in the sense that the third party, which is completely unknown to you, anybody who has your service ID can do this. A quite malicious third party can also discover the guard node you're connected to. For example, if I have like a botnet, I can just DDoS guard nodes, and once the guard node goes down, and then you also go down, I know, aha, this person who is on this Onion service was connected to Tor through this guard node. Therefore, this guard node will know who this person is. And so if you're quite malicious and quite capable, then you can de-anonymize users, you know. And this cyber stalking primitive is kind of the, not necessarily required, but a helpful sort of first step in this sort of chain of exploitation. So we would like to not have that. Another side note, if you never tell your onion service ID to anybody, this whole thing is not a problem because there's no way to enumerate service IDs. The only way to know if an onion service ID is online or offline is to try to connect to it. The only way you can do that is if you know the service ID. So in the sort of ricochet refresh example, if you have your 10 friends that you want to talk to, then you need to share this information with them, and then you can just scrub the ID from the internet or just not post it on the internet. If you just share it privately, then arbitrary adversaries can't do this. It does rely on you also trusting the people that you have trusted with this information, but that's kind of assumed that you're adding them as a friend in your application, that you probably trust them in some level. So what we want, we would like authenticated peers who can connect to and communicate with each other within this network. We want unauthenticated peers to not be able to determine all these peers' online, offline status. But we also want unauthenticated peers to have a pathway to becoming authenticated. And so, yeah, you can't do all three of those things at the same time. And especially when the core functionality requires you sharing your onion service ID with potentially untrustworthy users. Like if I wanted to share with you my Ricochet ID, I would post it, and then I just have to trust that one of you people are not going to track if I'm online or offline without my even knowing about it. Because you don't even need to, like, in the Ricochet Refresh example, you don't even need to become my friend in Ricochet Refresh. All you need to do is try to open a socket to me, and you can just build this profile. So Gosling's solution, we basically spread our one onion services responsibility across more onion services. So we basically take the client authentication and authorization step and put that in one onion service. And once a client has been authenticated and we trust them, we give them a secondary real onion service where we actually do our communications with. So basically, the identity service acts as a gatekeeper. It will determine whether or not incoming connections we have a further relationship with, whereas the endpoint services are where the actual sort of peer-to-peer application-specific protocol communications happen. So again, in the context of Ricochet Refresh, your chats would go over the endpoint services, but the initial greeting saying, "Hello, I'm so-and-so from accounting, I would like to be a friend," that communication would come in through the identity service. So the nice thing about dividing the labor up this way is that depending upon your application, so I kind of mentioned beforehand, if I just have 10 friends and I only want to talk to them, I could share with them publicly on whatever service my ID. And then once they have been added, and I have given them all their own individual secret onion services to connect to, I can then just never run my identity service ever again. So even though that ID is up on the internet somewhere, if I posted it there, other adversaries cannot just arbitrarily figure out if I'm online or offline until they've been authenticated. And if I don't need to authenticate any new users, then I don't have to be running this service which has this potential leak. So it's ultimately giving users more control over the visibility. So in the instant messaging context, you can kind of think of like different sort of like visibility modes that you kind of are familiar with on applications like Discord or whatever, where like, you know, on Discord, if you say like, oh, I'm invisible or I'm available or like I'm active, whatever, like that's just sort of a flag that you tell the server to tell other people. Whereas in this context, you can actually be invisible to everybody else on the internet just by not running the service. You can even appear invisible to your authenticated friends if you just don't run your endpoint services. You can still connect to them by trying to connect to them in the same way that, like, you know, invisible to everybody kind of works in these applications. But by sort of dividing up all of the functionality in this way, you kind of open up these different scenarios, which may or may not make sense depending upon your application. All right, do I dare do a demo? So I have a couple of example applications, and these applications also exist in the source repo. They're basically very simple chat applications, which kind of go through the whole handshakes and sort of splits up into the 2 or 3 sort of steps, just to illustrate it. Okay, so basically I've got these 2 sort of REPL applications that we've developed. By we, I mean me. They have the exact same user interface for the most part. The one on the left one on the left is the C++ version, one which uses this sort of CFFI, which we've exposed via the Rust crate, and the right one is just the pure Rust version. If you're a developer and you're interested in sort of seeing how this works, how an actual application would use this library, does it work now? All right, 1 minute. I'll be right back. Okay. Hello. All right, thank you so much. So yeah, the Rust version is just better to look at because it's not C++. And I say that as a former person who loves C++. So anyway, they both have the exact same sort of REPL interface. This is a very basic chat application that doesn't have any features or persistence of identity or whatever. It just sets up a handshake and works. So first up, we're going to connect to the Tor network. Hopefully the text is big enough that you can see, but if not, oh well. So we're in a context on either side. The one on the left has succeeded in connecting to the Tor network through my phone. Temp. All my important files live in temp. And this one's the Rust version. Hopefully that one will also go. Well, it's getting there. What? Oh, did I? Wow. It's fine. Init context /temp/. I'm glad somebody's paying attention. C++. Okay, all right. And that one will init in the Rust directory. All right. Bootstrap. We're done. All right, now we need to remember what the commands are. We'll start our identity service. I'm going to save this off somewhere because this is much lower resolution than I'm used to dealing in. Nobody look. Okay. We'll start our identity service. So over here, we basically have published an onion service, which will now listen to incoming connections from other potential peers in the network. And this guy on the right will now try to connect. So we're going to request an endpoint, which is ultimately what you're doing when you are connecting to somebody's identity server. So here's a second. Yep, perfect. So the guy on the right is now has requested an endpoint, and now it went through and succeeded on a handshake, and the handshake is just basically ignoring this sort of special, pluggable authorization things you can do. It's just like somebody connected, great, I'm going to auto-allow them in, which you should not do in a real application, obviously. So server identity, handshake exceeded. Now we can start our endpoint associated with this user. Cool, I think. Great. Oops, great. So now I should just be able to connect to that endpoint, which was this guy. Goes through, does a handshake. For each of these different servers, they're both going through and doing the same sort of client authentication, verifying that whenever they say, hey, I'm so-and-so user, and this is my service ID, it goes through and actually verifies, yes, that is indeed the case. So now, the guy on the right has connected to the guy on the left, and now we can chat. Well, first I'm going to list the connected clients, so I can get that in my clipboard. List peers. List peers. Great. And now I can send a little message to the guy on the left. Trust me, I just said something over there. Hello, and it shows up on the right. So look at that, real-time communication, and I can respond. It's this guy. Obviously, a real application should have better UX than copy-pasting commands around, but, hello, in response, I am the Rust example. And hopefully that will pop in. Oh, God. It died. Oh, no, wait. Okay, one of them died. That's great. Well, what do? It's a flaky mobile network. Just pretend it worked. Everybody clap. All right, I got it. Thank you. So current and future work, we're basically working now on integrating Gosling into Ricochet Refresh version 4 with even backward compatibility with v3, sort of. Because of the aforementioned sort of cyberstalking problem, you can't have complete backward compatibility because then you just be implementing the same thing. But basically, v4 clients will be able to connect to v3 clients without sacrificing the sort of metadata resistance that we're trying to bake into v4, but not the other way around. And as part of that, I'm sure there will be further Gosling iterations and improvements as we actually try to integrate it into a real piece of software and not just examples and tests. Once that's done, after some months, we're going to be focusing on Ricochet Refresh version 5, which will be like new features that people want beyond just the basic sort of chat application experience. Things like emojis and inline images and all kinds of things. Maybe even group chat. Who knows? But that's what we're basically working on over the next year and a half. Here is all the links. Gosling itself, like I mentioned, is a Rust library. It's got tons of tests. It has tons of examples in C++ and in Rust. It has automatically generated CFFI using cbindgen. That is mostly good to use. Needs some tweaks. You can get Ricochet Refresh from ricochetrefresh.net. We do monthly-ish releases with just security updates for the most part on the libraries that we depend on, and as well as updated pluggable transports and bridge lines, so that if you are connecting to Ricochet, or if you're using Ricochet Refresh in a censored region, on a censored network, if you stay up to date, you will get all the latest and greatest circumvention tech from the Tor project. And finally, you can learn more about Blueprint for Free Speech, the organization which sort of owns these two pieces of software and does a whole bunch of other advocacy work and journalism and whistleblower protections at this URL as well. And with that, I am open to questions if there are any. Is somebody managing? I think there's a microphone. Please form orderly queues.
Yes. Yeah, just a quick question: how much overhead you end up enforcing? Like when having to authenticate every new or when authenticating every new connection as as its own service. Like how would that compare to just doing it the lazy way?
That's a good question, and it's a question that I've been kind of avoiding given how small our current user base is. I mean, not to say that we have a relative to big applications like Discord, we have a small user base in terms of actual active users. So Ricochet Refresh, all we really know, because it's an anonymity-based chat platform, is how many monthly downloads we get off of GitHub, just because that's stats that GitHub tells us. And we've had like 12,000 unique-ish downloads in the past year. So from my perspective, the scaling question is one I've not worried about, because if it gets to be a problem, then we'll have succeeded beyond our wildest dreams. And it will ultimately not be my problem. It'll be the Tor project network team's problem.
Oh, yeah, thank you. My main concern is if you can get it on a Raspberry Pico.
I'm sorry, can you say that again?
If you can get it on the microcontroller in any way, then that opens unbelievable things.
Yeah, definitely.
In a different way. Thank you. Amazing.
Okay.
Maybe I have one more addendum in terms of embeddability, just based off of, hold on. So this example application just has basically just Gosling and some terminal stuff. And the Rust version is 5.5 megs. It might be able to be reduced more, but the C++ version is gigantic just because it pulls in like other stuff and it's not a real application. Don't look at it.
So one of the things that I've sort of really struggled with of all the messaging apps built on top of Tor is the necessity to be online. Is there any work on being able to like publish things to an address and then have that client at different times collect it?
So that's not
is
really...
there a store and forward, anybody trying to do store and forward?
So that's, in the general case, that's not really a problem that... It's not a problem we can solve. It's not, but I think it's more fair to say it's a problem we choose not to solve. So the Tor network itself does not have any mechanism for a sort of like messaging box system where like I have an identifier and I send a message and it goes somewhere within the Tor network, and then once I log in as the recipient, I can go and see what messages are available. Like that sort of functionality doesn't exist. You could, of course, build an application with a server component which allows people to run sort of a network within the Tor network of decentralized mailboxes to receive and messages in a sort of like offline manner. And I think Kuch itself, so Kuch is another messaging application. They have group messaging, which is somehow built off of this type of thing, where you're expected to run, and hopefully the Kuch devs don't come at me because I might be getting this wrong. But they're nice. But you can have sort of this always-on infrastructure as a volunteer. So again, not part of any big organization. Like I could personally run a always-on server, which would act as a sort of proxy to receive messages and then forward them on to me, to my mobile client. But we have tried to keep Ricochet purely peer-to-peer as a sort of a design constraint. It's because that is the sort of expectation of our sort of users and target audience. Like our sort of target audience is journalists and whistleblowers. And so like we definitely don't want either of these people having to run and maintain server infrastructure for basic functionality of the application. So with Ricochet Refresh, you just run it and it's running on your device and it just works. But it does make our lives harder because obviously having offline messaging would be a really big usability one, but then that just adds more complexity. I hope that answered your question.
I have one question. I've been looking for peer-to-peer applications on Tor. I've been looking into RT quite a lot because I think it has a lot of features that makes it far better suited to build applications on top of Tor. So are there any plans of like pushing that advantage or building tools like Ricochet Refresh on top of RT?
Yes. In fact, Gosling has RT support partially. It has in-proc RT client support, which in itself isn't exactly a supported sort of usage of RT yet, but we also have plans for out-of-process RT in a similar way that we have out-of-process Tor support. So as of right now, it has the RT client backend has full feature parity with the Tor daemon backend within Gosling. So as a Gosling consumer, you can build Gosling with this flag, use the right Tor provider, and you'll never have to worry about the legacy CTOR at all, which will make packaging people very happy, I'm sure. Anyone else? I'm here for 6 more minutes. Well, it doesn't look like there's any more questions. I think I can hand it back to the event people.